All right, folks, it's Bass Action, back in action here. In this video, we are going to go through the extended ratio, how they're developed, for another special right triangle, and it's the 45, 45, 90. Again, not creatively named. It's simply based on the measures of the angles and that a pattern exists for all triangles that are 45, 45, and 90. So we're going to first develop the quick extended ratio for that type of triangle, and then we're going to look at some examples. So starting here with the picture that I have here, I've got a square here. So I'm going to give you the fact that this is a square, which means the two sides are of course equal, and I have a right angle. Since it's a square, these would also be right angles. So when I draw on that diagonal, I know that each of the pieces will become 45 degrees. Now, what I want to do is I want to look at the triangle itself that's formed here. So again, we could look at the one that's on the top, or we can look at this one on the bottom. It doesn't matter. They're going to be the same. And we want to get an expression for the diagonal in terms of x. So we're just going to do a quick Pythagorean theorem again. So I'll have my d squared equals my x squared plus my x squared, which means d squared equals 2x squared. Now I'm going to take the square root of each side. Again, when these are multiplied underneath the radical, I can split them apart into their two values. So I'm going to have a d, I'll have a square root of 2 times an x. So I can now replace that, square root of 2 times x. Now I'm going to grab those coefficients, the coefficient on the hypotenuse. Remember, there's a coefficient of a 1 and a coefficient of a 1. So I can write those as the extended ratio of a 1, 1, and a radical 2, where the two ones, each of the ones, are going to represent the legs, and the square root of 2 will be for the hypotenuse. Again, flip to the inside of your foldable, and now we can look at a couple examples related to 45, 45, 90s. These are going to be easier than the 30, 60, 90s because there's fewer numbers to keep track of. I'm writing the extended ratio again up here at the top. Remember, as we go from the left to the right, we're going to multiply. And if we go from the right to the left, we'll divide. So taking a look at our first example here, you can see I have a 45, 45, 90 triangle, because if this one's 90 and this is 45, then this would have to be 45, which means I've started you off with a leg. That means that the other leg is very easy. We can get that without any math. And then we can get to the hypotenuse by just remembering that we want to go from a leg to the hypotenuse. So looking at our extended ratio, we're going from here to here. So we're going to multiply by a square root of 2. So we'll take our 9 radical 6 times our radical 2. That's going to give us a 9 radical 12. And of course, we need to simplify that 9 radical 12. And this one I am going to go ahead and write out for you. Remember, 12 is going to be 4 times 3, so it'll be a 2 that pops to the outside. So our hypotenuse is going to become an 18 radical 3. All right. Then we're going to go the other direction. On our next triangle, we're given the hypotenuse. So now we want to go from the hypotenuse to a leg. Both the legs will be the same, so it doesn't matter which one we're thinking about. So we're going to take our 14, and this time we're going to divide by the radical 2. Again, let's look at our extended ratio. That means I'm starting here, and I'm going backwards, so I need to get smaller, so I'm going to divide. As we mentioned before, we need to rationalize this, so we'll multiply top and bottom by that radical. That's going to give us a 14 radical 2 over 2. Of course, the 14 over the 2 reduces, and that gets me to a final answer of a 7 radical 2 for that side in the triangle, and both sides, both legs would be the same. The last one we'll do is a look at a little word problem here. We have a baseball diamond, but a baseball diamond is actually just a square. So if we have a nice little square, ooh, that's a terrible looking square, but you guys can play along. All right, so let's pretend we have a square here, which makes each of these sides 90. If I want to know the length from home plate to our third base, oh, that's supposed to say second base. Silly me. So I want to go from home plate to second base. So remember, because we would have home, and then we'd have first, second, and third. So we want to go home to third. So from home to third is going to be the diagonal verse square. This is also just like our proof from the previous page. We're going from a leg to the hypotenuse. So we just need to multiply by the radical 2. So we can very quickly get a 90 radical 2 without having to do a Pythagorean theorem and work with some really big numbers. So that's all that we've got for 45, 45, 90s. They're really, honestly, pretty quick. The key thing is to recognize and remember them so that you aren't trying to do Pythagorean theorem with some really big, obnoxious numbers.